So yeah, today we're going to last class we saw how to do sparse coding. Basically, if you're given a signal and a dictionary D, how do you obtain a representation alpha? Basically, how do you linearly combine the sparsely combine the elements in the dictionary in a way that you can reconstruct your signal, right? So today we'll see. Last class I was telling that standard dictionaries that can be used are DCT dictionaries and wavelet bases and things like that. We also saw an example of how to do one such optimization problem, how to solve the L1 L2 optimization. Basically, you have an L2 loss plus an L1 loss. The L1 loss promotes sparsity, and we saw one method how to reconstruct it. How to basically get the sparse code through this, through ISTA, iterative soft thresholding. And today we'll see, we'll close this loop of how do we get these dictionaries. So can we learn them from the data that we have, and we'll see how we can learn them. I'll teach you one such method, which is very simple and very well known. It's proposed by Professor Michael Elad. So in CS, so we'll see that. First, we'll define the problem, and then we'll recall how to do sparse coding, and then we'll see how do you do the dictionary update, and we'll see how to implement it. Won't go into details, but we'll see code. And then we'll go more into connecting the sparsity to deep learning, and which parts are lacking in sparsity and what deep learning covers. And we'll see one specific work which is very recent this year, called Deep Image Prior, which kind of generalizes how do you model these dictionaries. It doesn't mention the word dictionary, but how do you build optimal priors on your image, right? And then we'll see how to train such models. And there's code, but I probably won't have. I won't go through that. It's basically it's published by the paper itself, so you can just run. I'll just run you through it, but you can, and I can't run it because I don't have a GPU now. But you can go back and try it. It's a really cool paper. Yeah. So let's let's go back to last class. So let's say we have a signal X and we have a dictionary D, and we want a sparse code alpha, right? So this let's assume for now that this dictionary is fixed, and you want a specific sparse code which optimally represents your signal, and this X should be sparse. That is the problem setting of sparse coding. So this vector alpha is generated randomly with few non-zeros, and the dictionary is fixed, and we call each element of each column of the dictionary as atom. So the sparse coding problem is as follows. So you want to minimize the number of elements in alpha, such that you still get a faithful reconstruction, such that which means that your X minus D alpha is close to 0. And we discussed a couple of ways how to solve this problem, and also in the last class I'll recall one of it. So it's called orthogonal matching pursuit. Basically this problem is NP hard. So you have, which means you have exponential number of increasing possibilities with the increasing dimension, right? So that's why they mostly, if in image processing, they mostly apply this on patches, because you can't really apply this on whole images, because sparse coding it's an NP-hard problem. It grows exponentially, the search space. So let's see one method how to extract these sparse codes out of from the signal, and when you're given a signal and a dictionary. So it's as follows. So you initialize the support. You create something. We saw this in last class. It's just a recap. So we create a residual. So we keep adding atoms into our support until so that the error keeps decreasing. So first we start with the residual as a X, and we choose one atom alpha 1, which minimizes the error most. And it's a greedy scheme, because you're choosing one by one, right? So you choose the first atom which minimizes the most, and then you you have a desired level of sparsity. Let's say you want to pick 5 atoms or 10 atoms, and you pick until then, or if your error is small, you can already stop it. So this is one way of doing it. It's greedy scheme, and it's also very well used. Like we'll see how to use it for denoising today, for example. So one can also solve this problem by relaxing it to L1, L2 optimization instead of L0. You have L1 now, and we saw that in the last class. We also saw Alex also mentioned the derivation of this in the class. So we can solve this using a proximal operator with which is mentioned as S eta lambda. So this scheme is called ISTA, and basically the update step is and you keep iterating until you reach the alpha opt, right? So you have initial signal x, and then you project it with this operator, and then you multiply with this matrix, and so on. I hope you remember. So, but we're not using this today, so it's fine. So the thing is, where do these dictionaries come from? So so there is very careful line of research which is done on these dictionaries. How do you model them? For example, you can use DCT dictionaries and wavelet basis curvelet, and there's a series of works which have proven optimality, and you also there are some dictionaries which are optimal if you want to use specific set of signals, but there's a let's say you want, but the problem with all these approaches is they're optimal in the sense of all the family of signals you consider. But let's say you're given an image, it's not necessary that that the dictionary that you have from these models, let's say DCT or something like that, is optimal for this specific image, right? So when you have specific signal families, you can build dictionaries tailored to these families, which are more optimal than using a standard ones, right? And another thing is if when you use this actual DCT, for example, let's say you take a Fourier basis like DFT basis, you won't have a sparse support anymore. You have a very wide support. It's similar to DCT and all these model dictionaries. We want to build dictionaries which are specific to the signals we have in hand. If you have one image, then one image or a bunch of images. You want dictionaries which are very optimal for these signals, right? So so that is what was lacking in the standard the models that you put with hand. Like, okay, this element is it belongs to DCT and all that. So instead of that, we can directly take our inputs. We can train on them. How do you optimally model the dictionaries which fits this input? Or it doesn't matter for if you, depending on the task, you can build dictionaries. Let's say you're doing reconstruction, you can build dictionaries which are optimal for that. And it's not so trivial, but you can also do it so that you get your dictionaries which are optimal for classification and things like that. So I'll also briefly mention them, but not I won't go in depth. But you obviously now you have so we'll see one method of how to build such dictionaries which still maintains sparsity and will represent your data the best. Sparsity of the sparse codes are the alphas, and the problem now is you need to train them. You don't have like a fast transform. Like DCT is just a matrix multiplication. It's not as straightforward as that. You need to, when you get your input, you need to train your dictionary again, and then you and then you need to denoise, for example, if you want to use it for denoising. So, and these are of course not scalable, because if you want to do sparse coding, then I mean this dictionary learning steps involve sparse coding and dictionary updates, which in dictionary updates we have singular value decomposition of this dictionary. So these are not scalable. Let's say you have 32 by 32 patch. It's like 1024 elements. So you want to find a sparse code which is greater than 1024, which is like a lot of possibilities. So it's not so trivial extending them to big patches. For small patches, it's you can do it, right? So that's a problem, and yeah, it takes training and it's not scalable. So our dictionary learning problem is like this. Let's say you have your x is your set of signals. That's your training set, let's say. let's say if in the case of images, they are the set of patches you have. Let's say if it's 8 by 8 patches, then you have a bunch of 8 by 8 patches, and you have a dictionary which is a bunch of like a which is greater than, which is of course the number of columns are greater than number of rows, so it's redundant. So you have so now you want to now you want to get the matrix A, which is the set of alphas which optimally represents at this X, right? If you take, for example, the first column in X, so this these alphas basically, it means that the third element and the and the 10th element or something, they are being used to reconstruct these alphas and nothing else, and so on, like, or for all these so eventually, I mean, these steps you'll get it by sparse coding, and you want to you want your model to follow this, like d times alpha is X, right? So when you want to update, if you want to update your dictionary, it should follow that for when you do this, it should be when you want D and A in such a way that they should A should remain sparse, and at the same time D should be updated in a way that it decreases the error, right? So it should be as close as possible to X, the columns. So, but you want to update both of them and not remain the same. You want to be better than what you were before, in the before iteration. So how do you do it? So let's first recall. Let's first consider this scenario, k-means. So what is, let's say my dictionary is like a bunch of points in some space, and now I have a bunch of patches, and I'm doing k-means on it. What does it mean? So you're first taking each point and you're searching which point is the closest to all of them. So for example, X, this is my row is I took a transpose, so it's X transpose. Each row consists of one atom which is closest in dictionary D, right? This is like extreme form of sparsity. So now every element has a particular atom in D, which is the closest nearest neighbor. Let's call this sparse coding, right? And what you do next in k-means is you take each cluster and you find which atoms are associated with it, and you take a mean of them, right? So to obtain the new center. So that is the dictionary update. So and you do that. I mean, you basically look at each row in dictionary, and each column in dictionary, and then you find which atoms are associated with it, and then take an average of them and put them back in the dictionary, right? So so the algorithm that we're going to discuss is exactly in a similar setting, but except we will change this sparse coding step. And how do you update this dictionary? You don't want to just put the mean of them, you want to do something more, right? So this is the algorithm. It's called KSVD because instead of doing means, we're doing SVD. So and the rest is the same. Instead of doing nearest neighbors, which is too extreme, we'll do sparse coding using the algorithms that we pursuit algorithms that we learned in the last class and that we just saw, and we'll update the dictionary once you get these sparse codes, right? So I'll show you. The sparse coding step is the same, and so you get let's say this is one instance of sparse coding, but you can also do OMP, the greedy scheme that we talked about, and basis pursuit is another scheme. You can use anything you want, except that you want to typo. Okay, so except that you want you want to get a sparse code corresponding to each signal, right? You can use anything you want. So, and then the dictionary update step is as follows. So let's say you have a dictionary D, and you want to update each column of this dictionary, right? So now so let's say this is equal. Let's say this is equivalent to this. Basically, I'm just dividing the number of. I'm just writing it as an explicit multiplication of columns and rows. So now I want to update the jth column of the dictionary. So I'm just putting the rest of it into a different term because I don't care about the rest of the elements. I just push it in the forward term, like x minus whichever is not equal to the kth row. And now my error is this one, right? ek minus dk and alpha k. So I want to update the dk and alpha k such that they best represent this ek, right? Because I want this to be equal to 0. Is it clear? So if I want this to be equal to 0, close to 0, so I'm just writing this as a I'm just separating the atoms which are belonging to the kth column and the rest of the atoms, and I'm pushing the rest of the atoms to into X, and I'm writing it as ek, which is the which I will call as a residual. So now I want dk and alpha k, which which I want to update this dk and alpha k in such a way that it best represents ek, right? So this is exactly you want what now. What am I asking indirectly is basically I want the best one rank representation of my matrix ek. And how do you get the best one rank approximation is by SVD. So there's one caveat here. Basically, if you can't exactly do this because when you do this, it's not necessary that the alpha k that you get is sparse. So you will get a dense alpha k which you don't want, right? So how do you do it? How do you basically bypass this? So for each column in D, let's treat the update step as matrix factorization, and we'll do an SVD, right? So now the problem that we have is our dk is fine. We don't care if it's sparse or not, but our alpha k is not sparse anymore because it can be dense because we're not explicitly forcing it. So how do you bypass this? Is basically by just if you recall k-means, what does k-means do? It just chooses the atoms which are associated with a particular cluster, right? If a signal is not associated with a cluster, you don't care about it. So you don't consider it in the means that you do. So I'll go to this column k, and I see which signals are contributing to this particular column. So I see that all these blue columns, all these blue rows are, or it was columns. This is X transpose. All these blue rows are corresponding to this specific are using this specific atom in the dictionary. So I'll just bring them. I'll call this selection as omega. So now I have omega alpha k, which means I'm only choosing the red ones here, and I call omega ek as these. Okay. So I mean, previously I had ek. Now I'm choosing only the rows which are actually contributing to this specific dk, right? So yes, you have to do it for every column in the dictionary. Yeah, like exactly in k-means. In k-means you update all the clusters, right? So in here you update all the columns. So now I just now I have so I just I now I have this small residual matrix which I want to decompose into one long vector which is alpha k, and one long vector which is dk, and the small one is just the sparse elements of alpha k. I mean the non-zero elements. So this one I can easily decompose. It's also easy to decompose this. It's small. It just depends on the amount of sparsity I'm inducing. If I'm inducing a higher level of sparsity, I need to spend more computation. But otherwise, it's small, and it also preserves sparsity. Right now, you don't have to worry about if it's dense or not, because we're explicitly removing it, removing the non-dense part. So I'm getting alphas and decay, right? So if you putting this all in one, summarizing everything, so we had an initial dictionary D, which was which you can initialize with a hard dictionary or any transform or DCT or everything. We'll see in the code that we initialize one with DCT, and we do sparse coding on it. So we get for every D and X we get a specific alpha. Now you have D, X, and alpha. Now you want to update alpha and D. yeah, alpha and d given x, right? So and then you do this, and then you see go to every column in k and see which signals are contributing to it. Take a matrix factorization, basically do an svd and just pick the first singular value, singular value and the corresponding vector. So those will be your new d and alphas, and do it over and over. That's it. So if you, as you, what do we get in the end is basically an updated dictionary and an updated sparse code, which follows it. So and there are many papers, mostly from Mickey's group, which show that this can be used for many tasks. Like I'll show one on denoising, but you can adapt this same framework for even videos and for super resolution and every other image processing task, and it performs really well. So let's see how to code it. So so just I'm taking a image. Firstly, and then I'm adding some noise to it. I don't care about the details in the code. I'll just show you how the flow goes, and then you can read it later, right? So and then you want to now denoise the image. So I go here, I initialize my dictionary. I want to, so now when you have a, so how do you denoise an image? You get a noisy image. You build a dictionary with this noisy image. So if you remember, we in the previous class when we talked about, I think, BM3D, you also in the first stage of BM3D we build all this path similarity using noisy images, and we set just a threshold to be high, so that so here also we build the dictionary using our signals are noisy, and at the end, because of svd or and this sparsity, we get a denoised image. I'll show you. So first we build this dictionary using a noisy image, and I'm just changing all. I'm taking a patch size of 10 by 10. So I'll just write all of them in a column. Like now you have 100. I'm just writing everything in a column, so it's not patches anymore. And then you have many such elements in the dictionary, and I'm creating a dct dictionary of size, I think, I don't remember. Yeah, so of size 100 by 256. So after I build this dictionary, then I'm starting. Then I'm running in an iteration. I'm first running this OMP, which is the sparse coding step, and then I'm updating the dictionary. I mean, by updating the dictionary, when you update the dictionary, you're also updating the sparse codes, except just the values, not the positions themselves. The positions themselves are changed in OMP, and just the values of the sparse codes are changed in dictionary update. So OMP goes like this. So first you have you choose an empty residual, and then you keep adding whichever columns are giving you less error, and then you keep doing it until you reach the level of sparsity that you want. So this is the OMP loop. So and then in KSPD, we first go here, and then we pick a jth element in the dictionary, and then we see which elements are matching it. And then after, so one constraint that we have to follow in the dictionary learning is we have to always maintain the columns to be of unit norm, otherwise it won't work. So that's a condition. And so basically we just go to every element in this dictionary and then see whichever has at least whichever signals are contributing, and then we go to these signals, and we do an svd here. I mean, we create this error matrix, which is best stashing everything else other than the jth column. So you get this error matrix, and then you pick the zeroth element as your better dictionary element, and a zeroth element of u sigma v transpose. So you take the u0 as the better dictionary element, and the last one as the sparse code, the non-zero sparse code, and that's it. Then you get dictionary and the coefficient matrix. So I think it runs fairly fast. That's not too much, but then and then you do it for a few times, and that's it. Should take 20 seconds, I think. So the one major problem with this, as you can see clearly, is it can't scale. as your patches size grow, then you can't. It doesn't grow enough. So that's Alex taught you that you can. And also another problem is this patch averaging. So you when you replace when you essentially, okay, now we get, so okay, I missed something here. So we built this dictionary and image using we have new sparse code and the dictionary. So now when we get a noisy image, which is the same image in this case, but you can also train the dictionary on many images. So you get the sparse codes of this, and then you reconstruct using the learned dictionary, and then you get a denoised image, and then you place them, and by taking averages. Let's say you have each column, you're taking you're getting a patch, and then you keep moving like this, and essentially you place all the patches in the image, and you get a denoised image, right? So yeah, this was my original image, and it's fairly good. It's get like 32 dB on. So yeah, and what I was saying was the problem that you get is you're averaging the patches. You don't know how to deal with. You're basically losing everything about higher level information. You don't have any information about it. You're just dealing with them as patches. For denoising, it works because the noise is fairly local. But if you want to do any higher level tasks, let's say recognition, or any or segmentation or anything, it doesn't really work. So you have to. Alex taught in the class that you can do this hierarchical. You can do this multi-layer sparsity, which will kind of promote the lower level sparsity. Will deal with uh, will deal with the lower level features, and like exactly in CNNs, and the higher level, and as deep you go, you look at higher regions in the image. So but it's not there are no there are not many impressive results yet, but that's a limitation of the model. So so if you think about it now, so I briefly mentioned it in the last class, and I won't go deep in this class also about this, but you can, if you had in the previous class you saw that L1 L2 problem, right? So here you had some dictionaries here. Where's this? Yeah, you have this loop, right? Now I'm just removing this nd transpose and I minus nd transpose d, and I'm just placing some random matrices w, e, and d. So where's this? So W, A, E, and some random matrix S, and you can essentially you're getting a noisy input X, and you're basically running through this, and then you're getting a approximate sparse code, and then you're using a dictionary D, which you also learned before, to reconstruct X, right? If you think about it, you can think of it like it has some resemblances with neural networks. For example, you have a nonlinear encoding into an embedding space, which is your sparse codes. And here, okay, there are two things I want to say. So first thing is basically you can, if you render this W, E, S, and D as a random matrices, and I mean, you obviously initialize well with, let's say, D is dictionary, this D is DCD matrix, and these as random. Then basically you can think of all these things as weight matrices in your neural network, and you can just backprop through them. You can just mention that I want this loss to be minimum, and you can just do a back propagation and learn all these matrices in one shot without doing dictionary learning. Like you do a greedy step, and then you do a linear multiplication with a dictionary. You can just learn all of them in one shot. This was these were called unrolled networks. They're very fast because once you train this, you don't have to do sparse coding again when you're doing during inference. It just matrix multiplications, and then you get uh, and then you get your denoised input. So the second thing I want to say about this is you have some resemblance with neural networks, which is let's say if you replace this projection operator with a nonlinear projection, which is like a ReLU. So and if you have instead of a linear decoder, if you have something more complex, that something more nonlinear, let's say that takes this passcode to a signal, then it's essentially neural networks. Uh, so we s- so Alex showed more formally that you can convert this multi-layer sparse models into, you can think of them as a convolutional neural networks. So let's recall something now. So we where did we start from? We started from defining what is the best prior you can put on the image, right? So we started with initial priors like my Fourier domain should have less energy, and then we saw that patches was a good prior, and then we saw that dictionaries were good priors, like being sparse with respect to some dictionary was a good prior. So if you go back and see, this was what our I mean, we had an input signal X. We had some degradation, which was denoising, in painting, blur, whatever inverse problem you have, and you get some observation X. And now you want to restore the best in a best possible way the output, the input that was going into the degradation block, which was the clean image, and you want to restore this version of it using something. And what we saw until now was we want to enforce something that we know about the image on this while we are doing this restoration step. That is the prior on X, right? So yeah, so this can be written like this, and we saw many instances of solving these kind of problems. And we one of it that we saw today was this X should follow some sparsity with respect to dictionary, for example. Then you also have this total variation, which says that my image is piecewise smooth, and constraints like that. So what if you want to parameterize? What if you don't want to put explicit constraints on this X? Instead, you want to put some constraints on the things that make X. Let's say my dictionary. Let's say my X is a function called g of theta. Now I don't want to put my priors on X. I want to put my priors on theta, right? I want thetas in a way that I want theta in a way that this minimizes this energy, right? Just I'm writing X as g of theta. That's it. So this is exactly what we saw. So if you visually you can see that. So previously I'm saying that okay, reach this point X which has piecewise smoothness and all this stuff on X. Instead I'm saying that okay, now forget about what you have with X. Just you know that X is represented in a particular way using thetas, and now you put constraints on theta, like how should theta behave, right? So this is basically, I mean, I'm just creating some kind of an abstraction here and just parameterizing my image prior in a way. So one instance is what we saw today. For example, we can assume that my x is made of a dictionary D, which looks something like this, and theta is my sparse coefficients. Now I'll put a prior on my theta that okay, I want, given this dictionary D, I want my theta to be sparse, and I don't care about X because this dictionary will take care of X, right? So so but what is the problem with this model is we saw in this slide that we have a linear decoder. We don't have much expressiveness. It's our the possibilities that we can put on X is very constrained with this dictionary D. So we can't put the whole world in this dictionary D. So we would like to put it. So one idea that one way how we can put this is using CNNs. So if we assume that our G is a CNN, we know that CNNs have very good expressive capabilities. So for example, uh, I want to manipulate my theta, which was the sparse codes in the previous case. Uh, I'll just assume that, for example, my thetas are the parameters of a dictionary. If I can create such a model, such that it basically thinks that I have to modify these thetas in a way that I best perform in this task. Let's say my in this task, right? So so how do you do it? It's so you can just this is a very recent paper which is called Deep Image Prior. What they proposed is really simple. So you have now my g of theta. If I want to put a prior on if I want to put a prior on my image X, I can rather put it on this neural network theta. So which says the following. So x is I let's say I give x z as I parameterize this g of theta as f theta of z. Like z is some random noise that you give. My theta will be in a way that it will modify this random noise and it will give out something meaningful, right? So so, since g itself is a prior, we can get rid of this term r of g of theta, and we can just optimize for this. I want my thetas in a way that when I give random noise, it should be as close as possible to my corrupted input x hat, right? So this part is okay, but you have to note that I'm talking about a single image here. My x hat is a single image. I'm not taking a data set. I get a noisy image. I ask my neural network that when given a random noise, you get trained in a way that when I give you random noise, you should give out the denoised version of input x hat. Is it clear? So is there any question here? That's why I brought some sketches. So let's say you have your z input, right? And z is random noise. Let's say it's a uniform noise from -1 to 1. I want to this is my theta, which is a CNN. So I want to this gives out some x hat, right? I want this when given this, I'll represent this as g theta of z. I want this to be as minimal as possible, right? Yeah. So and I have only one example, right? I have only one noisy image. So that's it, and you can do such an experiment, and what you get as a so this x hat is a noisy image. This is all you have. This is noise, not even noisy image. It's just some noise. This is some image plus noise. X hat. The label is noisy image. I want to denoise something. Let's say I have only one image in my hand. I don't have a data set of them. So I have just this x hat, which is a noisy image, and I want my theta in a way that it takes noise, and it gets after training, it will be able to generate a denoised estimate of this of x hat, which is kind of counterintuitive. I'll show you how they trained it. So you don't have a label of denoised image, for example. So you can just initialize this z with some random noise between -1 to 1, and you want to minimize this. So essentially, when you have this, you can obviously use gradient descent, which is just very elementary mathematics, and just take derivative with respect to theta and then back propagate through it, which is chain rule. So it's and then we get some x hat, eventually after this converges, we get some x star, which is a denoised estimate of this. So why should such a thing work? So it's because of the following observation. So let's say my z was instead a clean image, then I'm reconstructing also a clean image. Then it is very simple for a neural network. It can express it really well, and you see that the convergence is really fast. If my z was instead x plus noise, so then the convergence will be a little slow, but still it will be able to converge to something meaningful. But if I shuffle my pixels, let's say this is my shuffle pixels, and the funny part is, even here, that if you give a single example in your training set, you have shuffled inputs at your input in your input, and you want to reconstruct the image, the neural network can reconstruct it, because you have only one training set. it has a good expressive power, so it will be able to converge to a zero error. And if you give a noise, and if you have if you ask it to reconstruct something, it can still do that, which is kind of counterintuitive because convolutions are just searching for correlations in the neighboring pixels, but eventually after training, it has the expressive power to reconstruct x hat, right? So that's why I'm talking about a single image in my data set, right? So my input, and I can get a clean image from it. So now, uh, the surprising part here is when I train with this random image in the at the input, and I try to reconstruct a noisy image at the out uh, random image in the input, and I can reconstruct a noisy version of this. If I do some early stopping, like if I don't let it first, the cool thing is when it tries to learn, before it overfits to this noisy version of the image, if you early stop it, like if let's say you stop it before it converges to zero error, it is basically reconstructing a denoised version of the input, which is a really cool thing because uh, which what does it mean by reconstructing a denoised version of the input? The network is able to put a very good prior on the noise in such a way that it first reconstructs the clean image x, and then it learns to add noise to it, right? So you can, this is for denoising, and for super resolution you can just change it a little bit, instead of forcing it to give predict a noisy image, you ask it to predict an x in such a way that when you okay, so I'll remove this. When you downsample this x hat, you get a low resolution image, right? I have only the low resolution image in my hand. Now I want to now I give network a random input, and I want to I'm asking it basically give me such an x hat such that when I downsample it, it should be a low resolution image. So and then in this case, you don't have to really downsample. You don't have to early stop or anything, but just doing this, you can get essentially this noise gets converted to something high resolution, such that when you downsample it, you get a low resolution image, which is exactly super resolution, right? So this is also kind of surprising. And what else it can do is basically when you skip some pixels in painting, like we saw in patch match, where we had the scribbles on the image which weren't having any information, we just say that okay, construct the rest of the image, this m is your mask, construct the rest of the image faithfully, then it is able to put semantic information in these in the areas where it was missing, right? So I'll show some results. So initially I'm giving it this. So after 100 iterations, I'm training this. After 100 iterations, you get something very meaningful. And as you keep training until 2,500 iterations, you're getting a very clean estimate from just noise. You're giving noise. You don't have a data set. You have only one label, and you're able to get something really cool. So this is and it kind of outperforms the KSPD and BM3D and everything that we learn. So which is funny because so even in super resolution, you just keep training it. After 1900 iterations, you basically get this x hat to be super resolved image. Okay, this early stopping is just for denoising because you don't want the network to learn the noise itself, so you just stop it early. So it just depends. You just keep printing out the images and stop it whenever the dB decreases. So you see when the overfitting happens. So yeah, it's not very well understood like when to stop and all that, but yeah, but it's cool. So you see that this in super resolution, it's almost as good as training a how else can you train a network is basically you can just give it you can just give a CNN my low resolution input and the high resolution input, and brute force it with 10,000 samples, let's say. Then also you can that's how standardly CNNs are trained. So you see that training on just one example without having a ground truth is able to approximate pretty well. And this is my corrupted image, and yeah, this is where you do the early stopping. So you give noise, and you give a noisy image at the output, and then exactly you stop it after a few iterations. Then basically it's learning to the output was getting this, and then it was learning to put the noise, right? In painting, and see that the semantic information is getting filled here. A lot of cool stuff. So I mean, this we were doing using patch match by matching patches and in a fast way and all that. But here you can just and then we were propagating information, if you remember. But here it's just training a CNN, and so and here what else? Since your prior is just the network structure, it heavily depends on what network you're using. In the so if you're using some these are some standard architectures of CNNs, like encoder decoder networks, where you have a downsampling track and following by the upsampling track. Then your then the results are different when you change the network to resonate. The results are different. It kind of also tells you which architecture is most suitable for an image. So so and yeah. So yeah, so this is a really cool paper, which is and you have code to test it, but just that I don't have a GPU, but it's really simple. You can train it in 5 to 10 minutes if you have access to a GPU, and it's it works really well, and that's it.